Okay. What we're going to be talking about today is Norton and Thevenin equivalent circuits. Now, what we've talked about this week and a little bit of last week was, what do you do when you have a bunch of resistances doing whatever? You know, here you can take this circuit and simplify it down to an equivalent resistance, okay? And that's our way, using equivalent resistance, of being able to figure out what the power supply is doing and what the load on the power supply is, how much power is being given by the power supply. Equivalent resistances is a great way to just represent the entire system very simply so that we can do quick calculations, mostly on power. How much power is being consumed in the system, how much power is being provided to the system. Those have to be equal. But that's where we stand here. So the interesting thing that we have is, what happens when I want to plug into a circuit like this? What happens when this is some circuit, but I also have terminals popping out of that circuit? Like maybe it is it's itself a power regulator, and coming out of this power regulator is a power outlet, okay? And oftentimes the way that this is represented is like this. I have terminals just sticking out of my circuit, and I will plug something into those terminals, and I will get some kind of behavior out of it, okay? It's basically, I'm going to be using this circuit to power a different circuit that I haven't decided yet. The math for this starts getting a little ugly, because let's say across VA, across this gap, I want to plug in just one resistor. Well, as we've talked about in class, that now puts this resistor in parallel with this one, which changes the equivalent resistance between these two nodes. And by doing so, we have now changed the total resistance that is seen by this power source. So, and if I want to change this resistance, pull it out and plug in a different one, it's going to change this resistance again, change the entire equivalent resistance, change the whole circuit. This is a very challenging problem to be able to use this type of a system, plug any kind of resistor in, and try to figure out algorithmically what is the behavior going to be for the system after I plug that component in. But we have some tools that we can use to really figure this out. Before we get into that discussion, I'm going to give you two definitions. Okay, the first definition I'm giving you is called open circuit. Now, in an open circuit, if you're just looking at, say here's a battery, and that battery is connected to a resistor, okay? The idea behind an open circuit is that it is an area of a circuit where a voltage is present, but there is no current. Okay, well, what does that mean? Well, here I have a voltage present across this battery that is being plugged into this resistance. The moment I pull the battery out, I have a voltage present across the battery terminals. I still do. It's 1.5 volts. It doesn't matter if it's plugged into the system or not. There's always going to be that voltage potential. Similarly, if I have this right here, and I pull out a wire, and I go like this, well, these are now in parallel. This is also going to be 1.5 volts. Difference between these two. And the moment I connect this with a wire, there's now 0 volts connected, and I've shorted this end of the battery with this end of the battery. Great way to start fires, by the way. This is how you do it with steel wool. If you've ever seen that. Have you seen that? That's the principle of it, is that it's a very, very low resistance wire that suddenly experiences a lot of current that it cannot handle. But that's a different story. There is a finite amount of resistance in every single wire, which is why you don't have an infinite amount of current coming out of those batteries. But in any case, for an open circuit here, this is an open circuit. If you want to go ahead and take a little bit more complex circuit and draw something like this. So here's one circuit. I'm going to go ahead and add another component in parallel. And then, you know what? For funsies, I'm going to go ahead and do this. This is an open circuit right here. Why? Because there is a voltage present between here and here. But there is no current. Why is there no current? It's not connected. That's just it. In order for there to be a current, there has to be something that carries the current. So if this isn't connected, this is going to be an open circuit right there just because there's a gap. There's no wire. Any electrons that are running through the system are going to stop here, turn around and go back. Stop here, turn around and go back, because there's no way for them to run across that bridge. The bridge is out. Okay, so that's the idea behind an open circuit. On the other side, a short circuit is the other definition. It's a great movie from the 1980s. Great movie. Have you ever seen it? No. It's a great movie. Very cheesy. But this is an area of a circuit where current is present, but there is no voltage. So the exact opposite definition of an open circuit. Short circuit, there's current. Open circuit, there's voltage. One of them, well, both of them are missing something. So here, in this system, this here is a short circuit because there's no voltage drop across that wire. But there is current present. There's current going through that wire headed here. Now this isn't exactly a short circuit, even though, yeah, it's a wire. There's no current going to be going through that. So that's not going to be a short circuit. You could call this a short circuit. Or you could do this, and that's a short circuit. And now there is no voltage between this terminal and this terminal, this node and this node, which also means there's not going to be current flowing here. Short circuiting a circuit is extremely dangerous. Open circuits are not dangerous at all, really, because you don't have, well, unless you touch both terminals and then become a short circuit. But open circuits are everywhere. Anytime you have a battery, the two terminals of that battery have an open circuit at them, just by existing. It creates an electric field between them. It's a giant voltage difference. Battery terminals are naturally open circuit. Even if they're connected to something, those two terminals still exist. And because they exist, they can be contacted. or you could throw another component across them. Just by existing, those terminals are open circuit. Okay? The two ends of this, just by existing, if you were to touch both ends, you could close that circuit, but it is itself an open circuit just sitting out here. We could put anything across the two ends of that resistor and just plug in a wire. You know, you get a wire, you jump it around. You're closing that open circuit. Okay? So open circuits and short circuits exist all over every circuit. A circuit is actually comprised of a bunch of short circuits, open circuits, and components. Short circuits combine the components. The open circuits really are the components because that's where the voltage is. So with these principles of open and closed circuits, what we're going to take is we're going to say, now an open circuit exists everywhere on a circuit. Everywhere. You could do it between the battery, you could do it between every one of the components, you could do it between multiple components. Anytime you have a node in a circuit, which by the way, nodes you can put anywhere, as we've talked about, you can put a leader wire out of that node and then measure the voltage between those 2 points. You can always do that. Class. Nobody ever calls me. It's weird. You can do that with anything. An open circuit can exist anywhere. And we can pull an open circuit voltage out of anything. One of the reasons why I had you calculate nodal voltages is because understanding nodal voltages will allow you to understand, dang it, will allow you to understand what the voltage is in that open circuit. Okay, so if you know what this node voltage is and you know what this node voltage is, the difference between them is that open circuit voltage. So understanding nodal voltages gives you a good view into what really is going on as far as open circuits go. So this is the foundation of what we're doing here. If we want to pull power out of this system, we want to know what the node voltage is between here and here, okay? And as we pointed out, that node voltage is going to change depending on what the rest of the circuit looks like. Okay, you may have other resistors that you put in here, and it's going to impact how much power is being consumed. It's going to impact how much power is being put into each one of these resistors. Plugging in an external load across these two terminals, between this one and this one, or between this one and this one, or between this one and this one. Plugging in an external load between any of those nodes is going to impact the way the entire system works. So for us to sit down and say, okay, every time we're going to plug in a brand new resistor, we're going to go back through and we're going to have to calculate everything. It's exhausting. And it's somewhat unnecessary. We don't need to do that because we have equivalent resistance ideas. And that equivalent resistance idea effectively comes to, Thevenin came up with the theory that you don't need to know what the rest of the system is. You could take any two of these wires, put the rest of the system in a box so that it's invisible, and have just these two wires sticking out, and all you care about is the voltage between them. It doesn't matter what the source voltage is, it doesn't matter what this resistance is, this resistance. All we care about is what's coming out of here. Okay? if that's the case, then we can make a circuit equivalent to this one, such that the output voltage VA, where this is plus and minus, are identical between whatever this black box thing is and this circuit here that we just drew. Okay? Much like equivalent resistances, where you can replace an entire series of resistances with one single resistor, and it has the same behavior in the system. Here now, we're placing a bunch of resistors and a voltage source with something equivalent that's going to provide the same output, okay? And the two things that are most important about that output are how much voltage are between these two terminals when there is no resistance. Well, when there's no current flowing through them, which is the open circuit voltage, and how much current would happen between these two nodes if I were to plug in a wire, effectively creating a short circuit. Okay? If I know what those two are, and I can get the voltage to be the same between these two circuits, and I can get the current to be the same between these two circuits, then I have an equivalent circuit. And that is the Thevenin equivalent circuit. Thevenin equivalent, I'll write this on the board. Well, I'll write it under definitions. Thevenin is an accent. A Thevenin equivalent circuit is a circuit where open circuit voltage and short circuit current are identical. Between two open circuits. Okay, so here we have two open circuits. We have terminals that are open. Here we have another open circuit. If the voltage across those is identical, and when you plug in a wire between those terminals, you get the same current, those circuits are equivalent, effectively. We don't have to go through and calculate how the system is behaving every time we plug in a different load. Okay, we can get a consistent voltage and current out of that load. Okay, the goal behind this is we want to take a complex system, make it simple, and make it predictable. So that plugging in a load to that system doesn't require having to go through and calculate everything, just that small circuit. Okay? So a Thevenin equivalent circuit says, I'm going to take this big circuit here, and I'm going to make it look like this. And that's it. That is a Thevenin equivalent circuit. It has a voltage, V Thevenin, and it has a resistance of R Thevenin. Okay, and we have combined all of the voltage sources, all of the current sources, all of the resistances, everything, we've put them together into just one resistor and one voltage source, and nothing else matters. This uses the same principle as equivalent resistances, but it applies that also to now equivalent power sources. And this is an equivalent power source. We could plug in a resistance, we could plug in any resistance, and this will have the same behavior as whatever system we're trying to model it is, as long as that system only is comprised of a resistor. That is an important piece here. If you have a capacitor in the system, This no longer is valid because you can't model capacitance with a resistor, which we'll get to in a couple weeks. All right, so let's just play around with this system quickly to understand it a little better. Okay, so first of all, as it stands, this circuit has an open circuit voltage of VA, okay? Now, we've talked about Kirchhoff's voltage law. In every closed circuit, the voltages sum to whatever the power source voltage is, okay? Well, this isn't a closed circuit. This is an open circuit. It's the definition of an open circuit. But the principles still apply. If I were to draw a loop like this, I have to account for all 24 volts. Or all 12 volts, or all 20 volts, or whatever this power supply is. If VT is equal to 10 volts, okay? And let's say RT is equal to 100 ohms. How much voltage is going to be across RT? You have a guess? That's a reasonable guess. The issue is, let's play with Ohm's law a little bit. Okay? V RT is equal to IRT times RT. How much current is flowing through that resistor? Huh? It should be 0.1, right? Should be. Problem is, there's no place for current to go. This is an open circuit, which means this experiences no current. Which means we can't have any current going through RT. Which means IRT for this circuit as it stands is equal to 0. Which means it doesn't matter what RT is, VRT is going to be equal to 0. There is no voltage across that component because there's no current. And yes, that's not intuitive, but what that also means is that if you have a battery and you plug in whatever, and then this end of the battery comes disconnected, you now have no voltage in the system. That's understandable. Your entire voltage in your system goes away because you don't have any power being supplied by the battery. You can't. Otherwise, you are generating power because you don't have anything going back into the end terminal of the battery. It's just free energy. It violates the concept of the law of conservation of energy. We can't have any voltage across this or we violate the law of conservation of energy. We can't. We can't have any current going through it. We can't have anything. Because that would require that same amount of current to be going into the negative terminal of the battery and coming out of the positive terminal of the battery. It would require that. That's not happening. So in this instance, VA, if we draw our loop, VA has to be equal to whatever VT is, because it's an open circuit. Okay, but what happens if we close it? If we close it, is that still going to be equal to VT? What do you think?
No, it wouldn't be, would it?
Why not?
Because you have a resistor that it would have to pass through.
Right. Here, the moment we close it, we have a pathway for electrons to travel through the circuit. So the moment we close it, now there is a current flowing through that resistor. And that current is no longer 0. Okay? That current is something. We now know what the resistance is. We also know there's nowhere else in this circuit where there's a voltage applied, because this is a short circuit. We've short-circuited that terminal, which means that the current flowing through it is equal to IRT is equal to VRT over RT, which VRT for this system is just equal to VT. Okay? So now we know a few things. The reason why Thevenin made this be his equivalent circuit is because these relationships are very simple. This is it's an easy pass. Okay? If we know what the voltage is between any two terminals in any circuit, and we know how much current passes through if we were to short those two terminals, we then know what IRT is, and we know what VT is. And really, we can figure out RT because you know 2 of 3. So that's the principle behind an equivalent circuit. We can represent any two terminals coming out of a circuit as a Thevenin equivalent circuit just by figuring those out. Now that's it's kind of gross, but we can make it work. Now I'm going to go ahead, and I also mentioned at the beginning that it's I mentioned Norton equivalent circuits. What's a Norton equivalent circuit? Well, it's a little bit different than a Thevenin equivalent circuit, but they're very much the same. A Thevenin equivalent circuit looks like this. A Norton equivalent circuit looks like this. Instead of having a voltage, a DC voltage supply, this now has a DC current supply. How is that different? Well, it's actually very different. I'm just going to call this our question mark for now. We'll come back and figure out what that resistance is. If this is going to be equal to whatever the circuit has, and this is also equal to it, these two have to be equal to each other. So when there is nothing connecting these two terminals, we have an open circuit between those two terminals. When we have an open circuit between those two terminals, what is the voltage here? It's Thevenin. It's this, right? It's whatever we figured out from the circuit is the voltage between those two terminals, okay? How do we figure out the voltage between the two terminals here with nothing connected? Well, we do have one closed loop. And we're loading it in parallel, whereas over here we're loading it in series. Now that's a big deal because if you remember from last time when we introduced current-driven sources, a current-driven source where you load things in parallel, it decreases the amount of power that's coming out of the source. In a voltage DC source, when things are loaded in series, it decreases the amount of power that is coming out of the battery. So these are functionally equivalent because both, just simply by creating a load at the terminals, you are utilizing some amount of power. And you are reducing the power produced or required by the circuit. Okay? So we need VA to be equals to VT, or whatever the voltage is in this circuit that we're looking at. Okay? In order to do that, what that means is that IT times R, whatever this is equal to VT. Because the voltage across this resistor, this R question mark, is the voltage between those two terminals. It's the voltage between the nodes, it's VA. So we need that to be true. But we also need it to be true where if we plug in a short circuit wire between both of these terminals, that it has the same current. Now we know for this system that current, IRT, is equal to VT over RT. We just derived that a little bit ago. With that equal to VT over RT, well, if we short this, how much current is going through that shorted wire? I mean, that's reasonable because you'd expect some to go through here. But imagine this, okay? You're going to a buffet, and it's a free buffet. And in one part of the buffet, you can spend $100 to buy a piece of pizza that happens to also be over here on this side. You're not going to spend $100 to get something you can get for free over here. So there's not going to be anybody spending $100 to buy a pizza here unless they really pity someone. Everyone is going to be going through the other line.
So it'd be all IT on the outside loop.
Yep. None on the inside loop. Why? Because there's no resistance. Current favors no resistance. Voltage favors resistance. Current favors no resistance. Okay? Another way that I like to look at an open circuit is here, this wire can be thought of as a resistor where this resistance is equal to 0 ohms. Okay? If we plug that in, this resistor is now in parallel with that resistor. So Req is equal to 1 over R whatever plus 1 over 0. 1 over 0 equals infinity. So here your Req is equal to 1 over whatever that R value is, doesn't matter, plus infinity. Well, I mean, you're not going to get less than infinity by adding them together. So this functionally is equal to 1 over infinity. 1 over infinity means that your equivalent resistance is equal to 0. So a short circuit wire itself can be thought of as a 0 ohm resistor. And it makes the math work out. If that's an easier way for you to think of it. A short circuit is 0 ohms. An open circuit, if we were to replace this with a resistor to create an open circuit, okay, you can think of this as an infinite resistance resistor. Now that's not realistic because it turns out we have dielectric and air. If you have two power terminals that are high enough voltage, it doesn't matter if there's a wire connecting them, electrons will jump, which is why you see arcing. In space, that doesn't happen because there's no dielectric. But in atmosphere, in every situation that we have, There is a dielectric, so you can't get an infinite resistance. There is a finite resistance, and it's the resistance of air. But we'll ignore that for now. We can think of it as this is an infinite resistance resistor. Okay? So if we want to take and make this an open circuit and put this in series with each other, well, we know that the equivalent resistance, Req, is equal to RT, whatever that is, plus infinity. Well, you're not going to get less than infinity by adding it, which means that your equivalent resistance here is equal to infinity. Okay? Now you want to find out how much current is flowing through this circuit with an infinite ohm resistor. IRT is equal to VT over Req. Okay? Req is infinity, so it really doesn't matter what VT is, unless VT is infinity also. But there's no real infinite voltage. That's not realistic. So what you end up with here is that your current is 0. Okay? Which makes this an open circuit. So an open circuit can be represented by an infinite resistance resistor. A short circuit can be represented by a 0 resistance resistor. Just fun ways of looking at the same thing. Okay, well anyways, I got diverted there. So if we jump this wire, we have 0 resistance between these two terminals now. We jump those two terminals. The total current, IT, has to be equal to the current generated by having this voltage divided by this resistance, which means IT is equal to VT over RT. Well, we saw that up here because that's the exact same equation. Turns out this question mark is also a T. It turns out that these two systems are identical. The current that is caused by jumping these two terminals is equal to IT for the Norton equivalent circuit. And that's how they're related. The voltage that is generated across this is equal to this times this, which is the equation for VT. They're the same thing, just two different ways of writing it. Okay, so again, this is the Norton and this is the Thevenin equivalent. All right. I think the best way to describe this is going to be through an example. Do you have any questions before I jump into that? Okay. Nobody else gets the ability to answer questions because nobody else is here. This is not easy stuff either. Okay, so with that in mind, we're going to go ahead and I'm going to take a quick break. And we'll come back and do an example to finish this lecture. So I guess we'll start up at 9:55.